Okay, welcome to exercise 3 on page 108. Most of the exercises we've done to this point have been very computational, and this is one exercise of a more theoretical nature, just to see if we can really understand the definitions of some of these terms that we're using. Okay, so let's read this problem together. They're starting us off with the linear operator, t from v to v. Okay, and we're assuming that the two numbers a and negative a are distinct eigenvalues of t. Okay, so t has at least two eigenvalues, a and negative a. And what we'd like to show is that the number a squared has to be an eigenvalue of the operator t squared, and that eigenvalue has to have a multiplicity of at least 2. Okay, so this is going to require us to put together a few things that we've talked about. All right, so let's start with what we're assuming here. Okay, we know that a and negative a are eigenvalues of t. Okay, so we know that they have to have eigenvectors. Let's give those eigenvectors names. So we'll let those be eigenvectors of t associated with a and negative a respectively. Okay, so again, those are just the eigenvectors that go with our eigenvalues. Okay, well, since those two eigenvectors go with different eigenvalues, we know that they're linearly independent. That was theorem 5.5. Okay, so the set that contains those two eigenvectors is linearly independent. Okay, now we're going to do a couple of calculations. Okay, we're trying to show that a squared is an eigenvalue of t squared. Okay, and what I'm going to try to convince you of is that that's the case, and that both of these vectors v and w happen to be eigenvectors associated with that eigenvalue of a squared. Okay, so here's the first calculation we're going to do. We're going to take and substitute v in to the operator t squared. And remember that t squared just means t of t. So t squared of v is just another way of writing t of v. Okay, and do we know anything about the pieces of this calculation? Well, t of v, we know that v is an eigenvector of t, and that its eigenvalue happens to be a. Okay, so by definition of an eigenvector, that means that t of v has to be a times v. Okay, so we know that that's true. And then because t is linear, we can take this scalar a and pull it outside. And then we come down to t of v again, but v is an eigenvector, and so t of v is av again. So we wind up with a times av, that's a squared v. Okay, there's one calculation. Let's do a similar calculation for w. Okay, this is going to break down very much the same way. We're going to get t of w, and we can ask the question again, what is t of w equal to? Well, w was an eigenvector of t, but it had an eigenvalue of negative a, which means that t of w is negative aw. Okay, so we can pull the negative a out this time. We come back to t of w, which we just said was negative a times w. And notice, when you do that multiplication, you get a squared times w. Okay, well, what's interesting about those two calculations is that a squared appeared twice. So we plugged in a vector, v, and what came out was a constant multiple of that vector. There's our proof that a squared is an eigenvalue of t squared. Okay, we plugged in a vector and got out a multiple of it. And the same thing happened for w. We plugged it in and got the same scalar multiple of w back. Okay, so what we can say is that v and w are both eigenvectors of t squared, and they both are associated with the same eigenvalue. Eigenvalue a squared. Okay, well, so what was it that we wanted to prove again? Okay, well, we wanted to prove that a squared was an eigenvalue of t squared. We've done that. Okay, and that it has a multiplicity of at least 2, which means that we can find at least 2 eigenvectors associated with it. Well, we kind of did that too. We showed that v and w are both eigenvectors that go with that eigenvalue. Okay, so to finish this, let's just see if we can support those kind of conceptual arguments with the necessary theorems here. So if we just give a name to the eigenspace of t squared associated with that eigenvalue of a squared, all we really need to do is to point out again that v and w are linearly independent. We proved that earlier in our argument. Okay, and since is linearly independent, we know that the dimension of that eigenspace is at least 2. Okay, and together with theorem 5.7, that proves exactly what we wanted. Okay, a squared does indeed have at least